May 1, 1962, 7:04 GMT. The Taurirt Tonafella mountain range, deep in the Algerian Sahara. 9 French soldiers from the 62nd 1st Groupe d'Armes Spéciales stood inside a sealed tunnel 1 kilometer beneath volcanic rock. They had been told this was the safest place on Earth. They were wrong. The nuclear device codenamed Barrel detonated with tremendous force beneath the mountain. The explosion should have been contained. Instead, the mountain split open like a cracked egg. Radioactive gases erupted from fissures in the rock face, billowing toward the surface. Within minutes, those 9 men were engulfed in a cloud of gamma radiation so intense that their dosimeter badges turned black. This wasn't supposed to happen. But then again, nothing about France's journey to nuclear independence had gone according to plan. How does a nation, shut out from the most exclusive club in history, abandoned by its wartime allies, and denied access to the technology it helped create, engineer an atomic bomb from scratch in one of the most inhospitable places on Earth? The answer lies not in Paris or Washington, but in the scorching sands of the Sahara Desert, where French engineers solved problems that had never been solved before. What they didn't know was that their greatest challenge wasn't building the bomb, it was surviving what came after.
Let's rewind to 1945. The war had ended, the Manhattan Project had succeeded, and France, home to pioneers like Marie Curie, Henri Becquerel, and the brilliant husband-wife team of Frederick and Irène Joliot-Curie, expected to be welcomed into the atomic age with open arms. After all, French scientists had contributed critical research on nuclear fission. Frederick Joliot-Curie had discovered artificial radioactivity in 1934. French physicists had identified chain reactions. When Nazi Germany invaded France in 1940, French scientists smuggled the world's entire supply of heavy water, 185 kilograms of it, out of Norway and eventually to Britain, keeping it from Hitler's hands. This wasn't just academic curiosity. This was the foundation upon which the atomic bomb was built. But in August 1946, everything changed. The United States Congress passed the Atomic Energy Act, better known as the McMahon Act. With the stroke of a pen, America cut off all nuclear cooperation with every nation on Earth, including Britain and France. The message was clear: atomic secrets would remain American secrets. For Britain, this was a temporary setback. By 1958, the U.S. amended the McMahon Act to allow nuclear sharing with the United Kingdom. Special relation restored. For France, the door remained firmly shut. Charles de Gaulle, who had returned to power in 1958, was furious. He saw this not just as a scientific slight, but as an existential threat. The Cold War was escalating. The Soviet Union had detonated its first atomic bomb in 1949. Britain joined the club in 1952. And France, despite its scientific heritage, was left standing outside in the cold. On October 18, 1945, even before the American betrayal, de Gaulle had established the Commissariat à l'énergie atomique, or CEA, France's Atomic Energy Commission. Frederick Joliot-Curie was appointed as the first High Commissioner. The goal was simple: make France a nuclear power, with or without American help. By 1952, the National Assembly had voted to fund a dedicated military nuclear program. But there was a problem. Actually, there were dozens of problems.
To build an atomic bomb, you need 3 things: weapons-grade fissile material, an engineering design that works, and a place to test it without destroying your own country. France had none of these. First, the fuel. Natural uranium contains only 0.7% of the isotope uranium-235, the kind that actually explodes.
To make a bomb, you need to enrich that percentage to at least 90%. The American Manhattan Project had used massive gaseous diffusion plants that consumed more electricity than some small countries. France didn't have that kind of infrastructure. The alternative was plutonium. You could breed plutonium-239 inside a nuclear reactor by bombarding uranium-238 with neutrons. But you needed specialized reactors designed for plutonium production, not electricity generation. And you needed chemical separation plants to extract the plutonium from intensely radioactive spent fuel rods. In 1954, construction began on France's first plutonium production reactor at Marcoule in southern France. The site eventually housed 3 natural uranium, graphite-moderated, gas-cooled reactors, designated G1, G2, and G3. These weren't power reactors in the traditional sense. Their primary mission was making bomb fuel, with electricity as a convenient byproduct. The first reactor, G1, went critical in 1956. By 1958, France was producing weapons-grade plutonium. But producing plutonium was only half the battle. You still needed to turn that plutonium into an actual weapon, and this is where things got exponentially harder. The physics of nuclear weapons is straightforward in theory. Compress fissile material rapidly to supercritical density, initiating a chain reaction. In practice, it's one of the most complex engineering challenges ever attempted. You need precision explosive lenses that compress plutonium uniformly from all directions. You need neutron initiators that fire at exactly the right microsecond. You need high-speed electronics that can coordinate detonation sequences faster than human perception. France had to reverse engineer all of this without blueprints, without American assistance, and without the benefit of decades of trial and error that the Manhattan Project had enjoyed. Leading the effort was a chemist named Bertrand Goldschmidt, who had actually worked on the Manhattan Project during the war before returning to France. He understood the principles but lacked the detailed specifications. French engineers essentially had to reinvent the atomic bomb from first principles. But even if they succeeded in building a working device, where would they test it? Nuclear tests couldn't be conducted in metropolitan France. The fallout would be catastrophic. They needed somewhere remote, geologically stable, and under French control. The answer lay 1,500 kilometers south, in French Algeria, in a region called the Tanezrouft, the most desolate corner of the Sahara Desert. In Arabic, Tanezrouft means the land of terror.
The French military chose a site near the town of Reggane, a dusty outpost where summer temperatures regularly exceeded 50 degrees Celsius. The Centre Saharien d'Expérimentation Militaire, or CSEM, would be constructed here. Think about the engineering challenges for a moment. This wasn't just building a test site. This was constructing an entire self-sufficient military-industrial complex in a place where nothing lived by choice. Water had to be trucked in daily from wells over 150 kilometers away. Every liter of water consumed on site arrived by convoy. Supply trucks traveled through sandstorms that could strip paint from metal. The fine Saharan dust infiltrated every piece of electronic equipment, corroding circuits and jamming mechanical systems. Construction materials arrived via a newly built 200-kilometer road from the nearest railhead. Cement had to be mixed immediately after arrival because the extreme heat would cause it to set prematurely. Concrete poured during midday would crack within hours. Workers labored in shifts, working dawn and dusk, sleeping through the inferno of midday. Accommodations for 6,500 French military personnel and engineers, plus 3,500 Algerian laborers, had to be built from scratch. Prefabricated buildings were shipped from France and assembled on site. Air conditioning units ran continuously, consuming diesel generators that themselves required constant cooling. But the real engineering marvel was the tower. For the first test, codenamed Gerboise Bleue, or Blue Gerboa, after a small desert rodent, the bomb would be detonated atop a 105-meter steel tower. This wasn't decorative. The height was carefully calculated to maximize blast effects for measurement while minimizing ground contamination from the fireball. Constructing a 105-meter tower in hurricane-force winds, where metal heated to temperatures too hot to touch by midday, required innovations in rapid assembly techniques. Sections were pre-welded in France, shipped in pieces, and bolted together on site using insulated tools and workers in protective suits. Simultaneously, 700 kilometers to the northeast, another site was being prepared beneath the Taurit Tan Afella Mountains near Inn Ecker. This would be France's underground testing facility, a network of tunnels drilled into volcanic rock for when atmospheric tests became politically untenable. Underground testing presented entirely different engineering challenges. You needed tunnels deep enough and strong enough to contain multi-kiloton explosions. Drill teams worked in temperatures exceeding 40 degrees Celsius, carving shafts up to 1,000 meters into solid granite. Ventilation systems had to be designed to extract rock dust and prevent suffocation. Elevator systems capable of lowering multi-ton nuclear devices into the earth had to be engineered and tested. Back in metropolitan France, the final piece of the puzzle was falling into place: uranium enrichment. In 1960, construction began on the Pierre Latte gaseous diffusion plant near the Rhône River in southeastern France. This facility would consume enormous amounts of electricity, requiring dedicated nuclear reactors and new transmission lines built specifically to power it. Électricité de France, the state utility, had to expand the national electrical grid to meet the demands of this single installation. Gaseous diffusion works by converting uranium into uranium hexafluoride gas, then forcing it through thousands of porous barriers. Lighter uranium-235 molecules pass through slightly faster than uranium-238, creating incremental enrichment. But incremental is the key word. You need thousands of stages cascaded together to reach weapons-grade purity. The Pierre Latte plant eventually consisted of 4 massive diffusion buildings, each housing miles of piping. The scale of France's commitment was staggering. Engineers, scientists, metallurgists, chemists, and construction workers numbered in the tens of thousands. This wasn't a science project. This was a national mobilization. And in February 1960, it was finally ready.
February 13th, 1960, 7:04 a.m. local time. The countdown reached 0. The device detonated with a yield of 70 kilotons, 4 times more powerful than the bomb dropped on Hiroshima. The fireball climbed 5 kilometers into the morning sky. The mushroom cloud rose to 15 kilometers. Seismic instruments in France, 2,500 kilometers away, registered the shock wave. France had joined the nuclear club. They were the 4th nation to detonate an atomic bomb after the United States, the Soviet Union, and the United Kingdom. But unlike those nations, France had done it entirely alone. No borrowed technology, no shared research, just French ingenuity, French plutonium, and French stubbornness in the face of American rejection. The bomb itself, later designated the AN-11, was a plutonium implosion device. It weighed approximately 1,500 kilograms. 32 explosive lenses, precisely machined and timed, compressed the plutonium core to supercritical density in less than 1 microsecond. The chain reaction released energy equivalent to 70,000 tons of TNT in a fraction of a second. International reaction was swift. The United States condemned the test. The Soviet Union called it destabilizing. The United Nations expressed concern. Charles de Gaulle issued a statement that dripped with vindication. France is now stronger and prouder. 3 more atmospheric tests followed at Reggane. Gerboise Bleue in April 1960 with a 1 kiloton yield. Gerboise Rouge in December 1960 with 5 kilotons. And Gerboise Verte in April 1961 with 1 kiloton again. These weren't redundant tests. Each validated different aspects of bomb design, miniaturization, yield scaling, safety mechanisms. But international pressure was mounting. Atmospheric testing was releasing radioactive fallout that traveled thousands of kilometers on prevailing winds. Algeria was approaching independence. The Evian Accords, signed in March 1962, granted Algeria sovereignty, but included a secret clause. France could continue nuclear testing in the Sahara for 5 more years. Testing moved underground to Ecker. This is where things went catastrophically wrong. The Beryl test on May 1, 1962, was designed to be fully contained. The device was lowered deep down a vertical shaft, sealed with concrete plugs designed to contain the explosion. Theory said the rock would absorb the blast, vaporizing a spherical cavity underground while producing 0 surface contamination. Theory was wrong. The explosion exceeded predictions. Cracks propagated through volcanic rock formations. Radioactive gases, superheated to thousands of degrees, found pathways to the surface. Vents opened. 9 soldiers from the 621st Groupe d'Armes Spéciales, who had been positioned near the tunnel entrance for measurement duties, were engulfed in radioactive vapor. Their exposure levels were never fully disclosed, but reports suggest doses exceeding 600 millisieverts, well into the danger zone. Several developed radiation sickness within hours. Long-term effects included cancers and genetic damage. The French military classified the incident for decades. Between 1961 and 1966, France conducted 13 underground tests at Ecker. Not all went smoothly. Beryl wasn't the only accident, just the most serious. But French engineers learned from each failure, refining containment techniques, improving geological surveys, developing better sealing methods. By 1966, France's nuclear arsenal was operational. The force de frappe, or strike force, consisted of Mirage 4 bombers armed with AN-11 and later AN-22 gravity bombs, each capable of delivering devastation comparable to the Reggane tests. Intermediate-range ballistic missiles were under development. Nuclear submarine programs were launched. All of it engineered from scratch, in defiance of American refusal to cooperate.
France's nuclear program didn't stop in the Sahara. Testing moved to French Polynesia in 1966, where 193 more tests would be conducted at Mururoa and Fangataufa atolls over the next 3 decades. The technology matured. Thermonuclear weapons were developed. Submarine-launched ballistic missiles entered service. Today, France maintains approximately 290 nuclear warheads, the 4th largest arsenal in the world. Unlike Britain, which relies on American technology for its Trident missile systems, France's deterrent remains completely independent. French submarines, French missiles, French warheads. No foreign veto power. No dependence on alliance structures. This independence came at a price. The environmental legacy of Saharan testing remains controversial. Algerian communities near Reggane and Ecker report elevated cancer rates and birth defects decades later.
France has acknowledged some responsibility, establishing compensation programs in 2010, but activists argue the measures remain inadequate. The Beryl incident and other accidents exposed thousands of French military personnel and Algerian civilians to radiation. Long-term epidemiological studies suggest increased cancer incidence, though precise causation is difficult to prove given the timescales involved. But from a purely engineering perspective, what France accomplished was extraordinary. They built an atomic bomb without American help, developed uranium enrichment and plutonium production infrastructure from scratch, and constructed testing facilities in one of the harshest environments on Earth. They solved problems that other nations had struggled with for years. How do you cool plutonium production reactors in a Mediterranean climate without massive water sources? How do you enrich uranium to weapons-grade purity without access to American centrifuge designs? How do you test nuclear weapons in the desert without destroying your own infrastructure or personnel? French engineers answered all these questions through innovation born of necessity. Marcoul's reactors used gas cooling instead of water. Pierre Lott's gaseous diffusion cascades were designed independently, though less efficient than American counterparts. Saharan testing protocols developed containment methods later adopted by other nuclear powers. The irony is that by the 1970s, as France's nuclear program matured, the United States began quietly providing technical assistance after all. Declassified documents suggest information sharing on submarine propulsion, missile guidance systems, and thermonuclear designs. But by then, France had already built the foundation independently. Charles de Gaulle's vision of strategic autonomy, the principle that France must never depend on others for its survival, was realized through the force de frappe. Whether you agree with nuclear weapons or not, the engineering achievement is undeniable.
The story of France's nuclear program offers lessons that extend far beyond weapons development. First, isolation breeds innovation. When American cooperation was denied, French engineers couldn't simply copy existing solutions. They had to invent new approaches, leading to unique reactor designs, enrichment methods, and testing protocols that influenced global nuclear engineering. Second, national commitment matters. France devoted substantial national resources and mobilized tens of thousands of people for over a decade to achieve nuclear independence. Modern megaprojects, from space exploration to climate infrastructure, require similar sustained commitment. Third, extreme environments demand creative solutions. Building in the Sahara forced innovations in heat management, dust protection, water logistics, and remote construction that have applications far beyond nuclear testing. Today's projects in deserts, polar regions, and even extraterrestrial environments draw on lessons learned at Reggane and in Ecker. And fourth, the consequences of technological ambition last generations. The radioactive legacy of nuclear testing, whether in Nevada, Kazakhstan, the Pacific, or the Sahara, reminds us that engineering decisions have ethical dimensions that extend decades beyond initial success. France's nuclear independence fundamentally shaped Cold War dynamics and continues to influence European strategic policy today. As the only European Union nation with an entirely independent nuclear deterrent, France provides a counterbalance to NATO's dependence on American nuclear umbrella. Recent discussions about European strategic autonomy echo Charles de Gaulle's arguments from the 1960s. From an engineering standpoint, we're still learning from France's experience. Modern small modular reactor designs draw inspiration from Marcoul's gas-cooled reactors. Laser enrichment techniques, now replacing gaseous diffusion globally, build on principles refined at Pierre Lotte. Underground containment methods developed at Ecker inform everything from nuclear waste disposal to asteroid deflection proposals. The engineers who built the atomic bomb in the Sahara weren't just constructing weapons, they were solving problems at the absolute edge of human capability, in conditions that pushed materials, systems, and human endurance to their limits. They succeeded. Against American refusal, Soviet skepticism, and the unforgiving Sahara itself, they succeeded. That tower at Reggane, vaporized in the Gerboise Bleue fireball, represented more than just a nuclear test. It represented what happens when a nation decides that independence, scientific advancement, and strategic autonomy are worth any price, any effort, and any engineering challenge. The desert sands have long since buried the physical infrastructure of France's nuclear program in Algeria, but the legacy, for better and worse, endures. If you found this deep dive into nuclear engineering history fascinating, subscribe for more technical military history content. Next time, we're exploring how Soviet engineers built an entire secret city in the Urals for plutonium production, including a reactor that exploded in 1957 in an accident the world didn't learn about for decades. That story and the engineering behind it is even more incredible than what you just heard. See you there.